Okay, I
Should I go
might
ahead?
no, I might get started. Welcome to everyone. Thanks for coming to today's ARC Center of Excellence uh, for Eco-Efficient Beneficiation of Minerals signature lecture. We have Heather Kaminsky from Northern Alberta Institute of Technology today. And I'd like to start by acknowledging the traditional custodians of country throughout Australia and their connections to land, sea, and community. And we pay our respects to their elders, past, present, and emerging, and extend that respect to all Aboriginal and Torres Strait Islanders people today. So with that, I'd like to introduce Heather Kaminsky, and she's the Queen of Clays. And we are happy to hear about her work in using methylene blue in mine tailings and planning in identifying clays, in particular, I think identifying clay types and behavior. So with that, go ahead, Heather. Thank you.
Yeah, awesome. And I would like to acknowledge that I'm talking from Treaty 6 territory in Edmonton at the moment. And that the traditional name for my homeland here in the city of Edmonton is Emiskwishi Waskagan. And would like to recognize the Cree, Métis, and other First Nations people in Alberta. So, and of course, all around the world. So thank you for your land acknowledgement, George. Um, yeah, so hopefully this talk is useful for you guys. We have been using methylene blue index in oil sands tailings management for a number of years. And I was introduced to this method as a PhD student, where I worked at CanMet for to do some of my research, and they were helping with troubleshooting, getting good data at that time. The downside of this method is sometimes troubleshooting is required, but it is extremely useful and provides really good kind of index properties or like rules of thumb that you can use to kind of predict a lot of pain in your process. So hopefully this talk will make that clear. All right. So,
Okay.
all right. So what are the signs that you might have a clay problem and that you want to pay attention to this? So this is one of my missions in giving converse or having conversations, particularly with folks like yourselves who are doing work on the front end of mining process. It's really easy when you're on the front end to kind of ignore those gang minerals and go, meh, we don't care. But they are actually incredibly important in maintaining that full life cycle for your mine and ensuring that you don't end up spending way more money than you planned in maintaining your facilities, closing costs, and of course, ensuring that you don't have tailings failures partway through your mine operation. So, what are some of the signs that you might have a clay problem? Are your facilities filling up faster than they have planned? Is it difficult to maintain your water clarity? Are your consolidation rates slower than you anticipated? Is your dike weaker than expected? Is it difficult to meet your underflow density targets? Or is your ore sticky? These are signs you may have a clay problem. Um, and so that begs the question, what are clays? And I like to start with this question because as a naive metallurgist starting my PhD, one of my supervisors said I was doing an entirely different topic. I was looking at the heavy minerals and I wanted to characterize them. And one of my supervisors said, well, you should look at the clays as well. And I'm like, sure, how hard can that be? And down the rabbit hole I went. And so, of course, coming from a metallurgy background where you are all about steels and like things are very defined by precise chemistry, I tried to find a good definition of clay and came up with this one from the Clay Mineral Society, which is the term clay refers to a naturally occurring material comprised primarily of fine grained minerals, which is generally plastic at appropriate water contents and will dried or harden when dried or fired. And I went, what? What the hell is that? This is useless to me. Um, and this is the official definition of clays. So yes, this is the definition that drives all engineers crazy. Um, so historically, we all kind of have this visceral understanding of what clays are, right? If you were as I used to do, digging to the bottom of the sandbox in your playground, you'd typically find a nice layer of clay that lined the sandbox, and that was fun to dig up and mold and play with. If you got to maybe do a pottery lesson, you got to play with the clays there. So we know kind of what it feels like to be clay by this term. But what does that mean from an engineering or practical perspective? Well, once we started actually defining minerals, so once the first microscopes and things like that were defined and the whole realm, I mean, you started by just classifying the shiny rocks. And clays were basically the stuff that couldn't be properly identified when it was bigger. And then when you get into petrographic thin sections, they defined that more closely of like, okay, it's the stuff that we can sort of see it, but we can't define individual grains within this because they're too fine. So we knew that it was this really fine material and it had these plastic characteristics. And so our definitions of clays have kind of morphed with our ability to measure them. And that's why measurement really matters. So our ability to characterize clays has changed with time. And our definitions, depending on where you go or who is trying to like slice and dice their ore, will evolve based on which measurement they mean. So clay was often originally a particle size term because you would just separate out the part that you couldn't settle after say 30 minutes or so, and you would calculate that from Stokes' law. You'd get, if you wanted to wait, I think it was the 30 minutes, that would be the 2 micron fraction. If you were a little more impatient, you might say, I'm going to wait 15 minutes. And I think that's around the 4 or 5 micron fraction. Don't quote me on that. I haven't done the math lately. But that's approximately that settling size. And that's really how it got to. It was like, okay, it's the stuff in this fraction. And we knew that that would generally be where it would have that plastic material behavior. You can have, of course, as we've learned with the advent of with X-ray diffraction, that there's a lot of things that are in that size fraction. So sometimes it's just small particles of other identified minerals, like quartz. You can have a lot of rock flowers. So you can have a lot of these really fine particles that don't have a lot of that plastic property. But once they got into it, you could find that, some were these more unique things that were these layered phyllosilicates and had this kind of plastic property to them. And that is what where we kind of come to in methylene blue. So three things you need to know about clays in general. One, clays are small. So again, that less than 2 micron fraction is the stuff that stays in suspension when you do that first initial size separation. So they're probably going to be in your flotation circuit in the water. They're not going to sink very easily. They can easily be trapped into your float, depending on the collector properties and things like that, and your concentrations of your fluid. Clays are not spherical. So you see lots of textbooks where people like to use spherical diagrams to represent particles. And that's fantastic for your rock flowers. It's fantastic for your blockier minerals like your quartz and things like that. It's terrible when you talk about clays. Clays are more like your sticky notes. So I forgot to grab my package of sticky notes for this talk. Oh, never mind. I have one. So I like to think of clays more like this booklet of sticky notes. And so typically you're going to see something kind of like this. And if I separate them all out, whoops. Where did my presentation go? Oh dear. I'm assuming it died on your end too.
Went to Google.
I don't.
Yeah, for some reason, I don't know why. Yeah, that's okay.
There we go. Got it back.
Thank you.
Okay. I must have hit escape by mistake. So yeah, they have these thin sheets, and so you have kind of chunks of these thin sheets, and therefore that plate-like tendency is really important because it behaves differently. It's going to have different tortuosity of path, and all of those things, and a lot more surface area than a sphere of the equivalent size, and that really matters when you get into measuring particle size, because if you're using a laser diffraction setup, remember that it measures differently than the equivalent settling diameter. So you cannot use the same cutoff. And I have a whole soapbox on that, but I'm not talking about that today. So they also have a charged surface. So these are not inert particles, and therefore they are going to interact differently with different fluids, and understanding that becomes really important to understanding their behavior. And this, my friends, is where the methylene blue index comes in. So what is the methylene blue index? So methylene blue is an organic cationic dye with a very high affinity for clay surfaces, specifically any clay surface that water would also like. So this is a fantastic water active probe. It basically measures a convolution of cation exchange capacity and water active surface area. And the binding coefficient of this dye for clays is ridiculously high, like 10 to the 8, as opposed to for sodium, you're at 1. So it essentially kicks everything else off of your clay surface, and fully in a dilute suspension will fully replace all the other exchangeable cations. Why we really love it in oil sands is it will also kick bitumen off the surface and kind of ignore the bitumen. And so there's a little bit of an impact for organics that are still left behind, but not as much as for some of the other techniques. So it's not as sensitive to residual organics as other techniques, and so that makes it great for our purposes. So methylene blue index is typically about 125 to 150% of the cation exchange capacity from other techniques. So you measure this as a milli equivalents per 100 gram, which is the same as you would do for any cation exchange technique, but it really is this convolution of surface area and cation exchange capacity. And for oil sands, they modified the ASTM test method and developed one that's specific to oil sands. And the key differences are reducing the concentration, just making it a little easier to get more accurate titrations, and really ensuring you have a completely dispersed sample. So those are the kind of some of the key things. So the key reagent preparation that we do is we make the methylene blue solution. We also have a sodium bicarbonate buffer that we use to disperse everything into. A little bit of sodium hydroxide also acts as a dispersant. And then we use sulfuric acid for the acidic addressment right before titration. And I can tell you that the type of acid matters in this setup. So we get a slightly different answer if you use hydrochloric acid versus sulfuric acid. So then you need to disperse your sample. And so we use a basic pH adjustment. We're trying to get to that 8 to 12 pH range. Usually 10 to 12 is really where we like to get to, like about that 10 to 12. We soak the sample to make sure everything is really well hydrated. We heat it to 60 degrees. Again, that's really more important in the oil sands where you have those organics and you're just trying to make sure that those are all loosened off. And then we mix it and we sonicate it. So these are, if you have like a sample that's like a coherent rock, you would want to crush it first to get like, you're trying to get at the fundamental properties here. Then you're going to titrate it, and you use we've used anything from a glass stir stick to get the dots out, and using a burette to add the methylene blue in sort of stepwise increments, or we can use a pipette to add the methylene blue in stepwise increments and then a pipette to get it out. And unlike a normal titration where you just add and you see the endpoint happen, you actually have to remove an aliquot and put it on a filter paper to do this visual halo detection. So what you're looking for, and it's very difficult to see in these pictures because we now have gotten to the point where we're calling an endpoint right at that endpoint, is you're looking for excess blue dye to show up around that central point. So the dark blue circles are the clay and the methylene blue are kind of complexed, and then the methylene blue will absorb to as many clay surfaces as it can. And then once there's excess methylene blue in the solution, that will stay in the water phase. And so you can measure that as it comes out in the aqueous phase. There isn't a UV detection endpoint, but that tends to require you to dilute the sample way further. And if you have bitumen in your sample, it messes things up. So that's partly why the halo method is the primary method used in oil sands. But because you are removing these aliquots, you do have to be careful to make sure that your endpoints aren't too high, because if you're too high, you've just removed a whole lot of material and that shifts your endpoint, like your calculated value. And you also don't want your endpoint to be too low because there's an error in the like you need to have had enough titration steps to make sure that you've added enough dye and that you have confidence in that interval. So methylene blue is used around the world. It's primarily used for the identification of swelling clays. That's really where it was developed, is for bentonites, and specifically I think it was originally developed for like the green sand casting space, but I'm not perfectly sure about that. Definitely for targeting swelling clays. And it's really great for determining if there's any of that in an aggregate sample for analysis of sedimentary rocks like mud rock and limestone. And it can be used for the suitability of that aggregate for filler in cement or concrete or other things. It's really just screening, does this have too much stuff that's going to cause me problems? That's where it's used mostly around the world. And in Alberta, it is used for mine planning in oil sands. So basically, every mine in the oil sands area measures the methylene blue index on the ore, and then they also do methylene blue index profiling of their tailings ponds annually, or almost all of them do. So how do we use this methylene blue data? So MBI provides this measurement of water active surface area, which is this, as I said, convolution of cation exchange capacity and surface area. And the methylene blue will increase as your particle size decreases and as your cation exchange capacity increases, because it is influenced by charge. So you cannot use this as a replacement to particle size measurements, although people have tried, and I glare at them anytime I've seen that. I'm like, no, do not use this. Do not try and do this. They will measure methylene blue, and there is a really bad habit in the oil sands where we've converted this through this empirical equation. They will convert it to a percent clay, and then they will try and make that match their percent clay by laser diffraction. And I just, no, two different measurements. You cannot do this. Please, please stop the madness wherever you see this. Do not do this. It should only ever be reported as a methylene, as a milliequivalents per 100 gram. You can do that like calculation in percent clay if you need to, but don't put it in a paper. If I review your papers with it in, I will get cranky. But it is, if you use it as this milliequivalent per 100 gram true like SI units, then it is very useful because it can be used in intrinsic property calculations. So this is really useful. Again, is it perfect? No. But if you're like, okay, I'm going to blend this stream and this stream, and I'm trying to figure this out before my mine is built, and I can't get at this stream, or let's say you're doing some lab testing and you're like, okay, I'm creating the tailings. What is the, what, like I've measured the clay in my ore, I've measured the clay in the tailings. Did I enrich the clay or did I make the clay go lower? Usually they're fairly intrinsic. So you can kind of go, I have this much clay coming in. It had, let's say, 100 kilograms of sample at 10 milliequivalents, and I have another 100 kilograms of sample at 5 milliequivalents. If I mix them together, I should end up with approximately 200 kilograms of stuff at an MBI of 7.5 if it's all nicely mixed. So that can be really useful for kind of, again, that back of the envelope prediction of combined properties. Or if you have two streams that you've measured, again, inferring what that third might be, or just looking for, am I concentrating anything up? Is there anything that could be of concern here? So why is this a very useful method for pain index? So this gets a little, hopefully this I can make sense today. We'll see. So mineralogical analysis of clays in particular is a pain in the ass. So I have spent way too much time with an XRD doing clay mineral analysis, and I have done, and we still do in our lab, we do the full size separation where we get the less than 2 micron fraction, and we prepare the oriented clay slides, and we subject them to the 7 different pre-treatments that are recommended by Moore and Reynolds in the Bible here for clay analysis, which is X-ray diffraction of clay minerals. This takes a lot of time and effort and energy to properly do, and it's still very much semi-quantitative. You can basically go, oh yeah, I have kaolinite smectite and I have illite smectite. When you do this on oil sands, you basically get the same general approximate values, and the error in the test is such that it's like, maybe this is good. Like, is A bigger than B? Like, that's all that you can really assess. So if you have a large database of clay mineral analysis by XRD, it can work the same way. It is very useful, but you really need to have the same operator do the analysis with the same instrument, because doing the analysis is way more subjective, in my experience, than doing a titration method. So this one still has subjectivity, but it's way easier to compare and validate between labs. So the other advantage is this test we can do about 6 or 7 samples in a day. To do all the size separation and everything like that for X-ray diffraction, you're looking at like 1 or 2 samples a day. So per technician and per machine, or per technician usually. So with the methylene blue, you can scale up that number of tests by just hiring a whole lot more operators in a short period of time. So this is why they can do 1,300 samples a year for each mine. Just have a blitz on people doing these tests, and they're fairly cheap to run. You know, you don't need somebody with a PhD to do the interpretation of the results. You can get somebody after a good chemical diploma, and they can run the test. MBI can also be performed on either solid or slurry samples, and they can, so you really do need to understand the range of your results, and this example here is really specific to oil sands. So typically our solid samples for ore, at least, I should have caught that earlier, I didn't. So ore solid samples are usually 0.1 to 2 milliequivalents per gram in oil sands, and the slurry samples are usually 1 to 15. Again, if you have a pure clay sample, and like if I take a bentonite and I run this test, I will get an MBI of 76 to 125. So it can be quite the range. And dewatering is really impacted if the so why this matters. So I'm actually going to go into this in a little bit in a few more slides. So I'm going to skip this comment right now. But we know that dewatering is really impacted by how much free water is there. So as the amount of free water declines in a sample, that layer that is surrounding all your clays is also getting thinner. And that means that your electrostatic forces from your clays, which are charged particles, are now going to have a higher influence on that water that's remaining. And so the removal of each subsequent layer of water becomes more difficult. And that's really critical for all of these tailings processes. So what is the importance of MBI? There is a linear relationship between MBI and these fundamental clay properties, such as clay cation exchange capacity and kind of this total clay content. Like if you do the XRD analysis and you figure out the total clays and you figure out their swelling index, you can calculate an approximate MBI, and that matches with what you get when you measure MBI. MBI is a simple index test, and it can provide that indication of activity, and it can be a really useful indicator. We've used it in oil sands to predict correlation to bitumen recovery. So if you have a high MBI, your bitumen recovery typically goes down. And the example of this is shown on the right here. So a really high grade ore in oil sands will typically have an MBI less than 0.5 in that ore. And so that means you just don't have that many clays. your flotation process is fantastic, and that total active surface area is about 4 millimeters squared per gram. That's another correlation from Hang and Brindley. Again, kind of a quasi like arm wavy correlation, but it gives us kind of a nice estimate, and that's, I find it a very useful theoretical construct to understand why the MBI is useful. So bear with me. For a low-grade ore, that still processes well, you're typically between that 0.5 and that 0.9. So you're almost double the amount of clays as you are for your high-grade ore, but the active surface area is still below about 7 or 8. And that number is really important. Once we get into a really poor processing ore, you're typically looking at MBIs greater than 1.5. So if you have an ore that has an MBI greater than 1.5, you will typically struggle to get flotation to behave well, or you will have to dilute it a lot more than would be typical in an oil sands process. And of course, they just don't have the sizing of tanks and stuff like that. Like if you have to dilute it that much, you're killing your throughput, you're causing a whole lot of other challenges. So they don't really like that. And that has an active surface area of about 12. Now, there's something really interesting, because in geotechnical literature, so if you pull out the Fundamentals of Soil Mechanics by Mitchell and Soji, there's a lovely comment about, well, clays dominate behavior if they are present in more than 30% of a sample. Great. But they can also dominate behavior if you have a 1% of a high charged, like a swelling clay, or like or not a high charge, but a highly swelling clay. You're like, cool. So somewhere between 1 and 30 is going to be my critical point. So I took that commentary and went, all right, well, what do I know about the surface chemistry and that sort of thing of these different streams? So kaolinite is typically our least active clay. So let's assume that I have a soil with 30% kaolinite and the rest is sand. A typical MBI for that mixture, I would estimate to be around 1, with an active surface area of about 8. Interesting. Okay. Remember, my low processing cutoff was about 8 as well. I was like, huh, that's an interesting connection. Did the calculation for about 1% bentonite. Again, I get the calculation to be around an MBI of 1, around that surface active area of 8. This has led me to the conclusion that I think if you have an ore body with an MBI greater than 1, your material is probably going to be influenced by clay. So if you have a soil or an ore or whatever, I would pay attention to the clay content if your MBI is above 1. And we have found in oil sands by experimenting, because we have all of this really great data on MBI, and then, well, you've calculated MBI and now you're doing all these other things. Let's start to see, are there any correlations that come out? Well, we've seen good correlations with yield stress, flocculant dose, tailings volumes, Atterberg limits, etc. And I'm going to walk you through some of those examples. So in flocculation, this is a really important one. Typically flocculation dosing, so we always do dosage curves for all of our samples in our lab. So this is data that is from one of our papers, and I thought I had the reference on here, but apparently this is the version that didn't have the reference on it. Maybe you could put the link to the paper in the chat. That would be fantastic. Yunhui wrote this paper. She did a great job. And so what we did is we took 3 different fluid fine tailing samples, and we treated them with the same polymer and got 3 different polymer dosage curves. That's very typical. But what's really interesting is when we then corrected them and put it on a clay-based dose. So we did what I say don't do, which is calculate a percent clay and calculate a dosage from there. But we've also, in the paper you see, and this is what Suncor does all the time. So that's why we did it this way. But we've also in the paper done it the more scientifically rigorous way of like calculating it by, I forget what we called it, but effectively activity-based dose. which is an MBI base dose. Same thing, different math. And you can see that the dosage curves now line up much more closely. So where we looked at where it looked like you had three very different dosages depending on the sample that you were using. So somewhere between 1200 for FFT2 and say 700 for FFT3 and maybe 1100 for FFT4. We found that we were around that 1300 grams per ton clay when you look at all of them on the same basis. So, and this has been proven. We've done this over countless of other examples, and it is really what Suncor uses in their day-to-day operations to calculate the expected average flocculant dose that they're going to need for the next year. So how do we do that? Well, we can calculate these milliequivalents of methylene blue. And sorry, I should have put this in. I put this in the wrong order. So we do our titration. We figure out the mils of methylene blue that we have, divide it by the mass of dried solids we added, multiply it by the normality of methylene blue, and that's where we get our happy SI values. And then here is this Hangen-Brindley correlation where we can approximate surface area. And apologies for moving around my slides at the last minute and not noticing that I put them in a strange order. Anyway, and just move that up. We've also found that we can link MBI and yield stress. So you can use MBI to calculate a clay to water ratio. So that's basically saying, all right, if I have this amount of surface area that I've calculated from my methylene blue, I'm going to assume that all of the water that I have is evenly spread around that surface area. So if I have 8 meters squared per gram and I divide all of my water by that 8 meters squared, what is the thickness of my water layer that I'm going to get? So that's this water layer index that we have here. Suncor has this bastardized version, which it is the original. It's great, but it uses all these like empirical correlations that really don't have scientific merit. They were useful empirical correlations for their mind. The water layer index is the one that's actually scientifically rigorous. Basically same thing, just different math. So here's the two graphs. And you can see that there's this lovely correlation between how thick that expected water layer is around my surface of the clays and what my peak yield stress is going to be. And this holds regardless of if I'm in the very thin dilute suspension region. It starts to break down as we start to play with more of the water chemistry. But if you have similar water chemistries for all of this, it holds even quite far down on that water layer, or like having lots of water. And then also holds all the way up into the geotechnical realm. So that's quite handy because now this is a single parameter that we can use to try and actually understand that whole behavior range from the very fluid, which is where we're processing everything, to the very solid, which is where the geotechnical engineers want to play. And this is one of the only correlations that I found that can actually get us through the tailings zone, as I like to call it, which is that 400 to 2500 Pascal range that the geotechs don't like dealing with because it's too soft, and the process engineers don't like dealing with because it's too solid. And so it's left to us tailings engineers to play with. Really interestingly is Locat and Deemer showed a very similar correlation with liquidity index. And this makes sense that the methylene blue would work because our liquid limit, which is the kind of controlling factor for a lot of liquidity index, correlates really well with that specific surface area and therefore with methylene blue index. So we've seen that as well. Although, like one of the caveats in this is your water chemistry also matters. So for Atterberg limits, it correlates as you have more surface area, your liquid limit will go up, but how much it will go up depends on what the fluid is that you're using to do that test. So a key caveat in knowing that. And again, this is this water active surface to water content correlation. So again, you can sort of see in principle, this applies for spheres as well as for platelets. Obviously, as you get smaller, the larger your surface area is per gram of particles, and therefore the larger water holding capacity. This is why the smallness of your particles matter in terms of how difficult it is to get the water out, because they just have more capillary places where water is going to be held. And that tortuosity of the path is going to go up, which makes it more difficult to get water out. So you can this holds for inert spheres as well as for clays, but clays make it so much worse because their surface area is so much higher than their equivalent spherical diameter would lead you to believe, because they have this holding capacity of water. So let's link that to our expected dewatering range. So some of the things that have been really interesting is I've looked at what the liquid limit range is and the plastic limit range is for a lot of different minerals in the literature. And we have methylene blue data for, again, in the literature for some of these, and calculated, okay, well, what is that approximate, like, is there a similar water layer index? And the answer was yes. So typically your liquid limit is going to be somewhere between 10 and 14 nanometers of water that you calculate on average. And that, I think, kind of makes sense. So that's the point where your sample is no longer going to behave like a fluid. It's going to be starting to behave like a solid. So it's still very fluid. Like I'm taking pottery classes right now, and they're like, yeah, this is too wet to really want to play with. I mean, you can start to play with it, but they're like, let it dry out some. And the plastic limit is harder to get a more precise range, mostly because by that time your error in water contents, the math starts to just make your error bars too high. But I think this is a really useful kind of like, oh, okay, that's a nice mental exercise. We know it's very difficult using mechanical dewatering techniques to get down into this liquid limit range. We like thickening, centrifuging do not get you into this range most of the time. You can maybe get there with a filter press into the liquid limit, but mostly you're looking at commingling or other techniques that add sand to get it into the into a better range where you need to have that. So now if we link our MBI to Atterberg limits, this is one of the key things that I love. This paper by Yang and Santamarina from 2015. Just beautiful. This paper made me super happy when I read this. The effect of pore fluids on the liquid limit for different materials. And this is really important for all of you doing flotation research, because you will note that they use 3 different fluids in these measurements: DI water, brine, and kerosene, which I know all of you also look at. And look at the difference in behavior when you have bentonite, where you have Atterberg limit with DI water, which needs, now it's 276% gravimetric water content, which is the mass of water divided by your mass of solids. Very confusing measurement for us process engineers, but it's what geotechs use all the time. So pay attention to your units when you're crossing that divide. But 276% water content, as opposed to when you use it with kerosene, it's 39, because bentonites do not like hydrophobic fluids. They're going to ignore it. They are going to stay with the water. They love their water buddies. They want to stay with the water. However, when you look at kaolinite had a liquid limit of 67 in that DI water, and then it goes up when you mix it with kerosene. Because guess what? Kaolinites have a lot of non-polar surface, and so they actually really like your non-polar collectors and are going to interact with them far more strongly than you would expect. And so this is kind of a really interesting aside. And this is why I say pore fluid chemistry matters when you're kind of connecting to Atterberg limits, but still you can see the general trend. So we know that Your surface area is typically the highest for your bentonites, and it's typically the lowest, obviously, for your silica flour. And then your kaolinites and illites, it can kind of vary depending on which structure it was. So I really do love this paper. Your Atterberg limits will also be influenced by organic contents and all kinds of things. So that's the other reason that as an engineer person who wants to try and predict things from the ore body and carry it through, doesn't always work perfectly, but at least to be able to conceptually prove that, I love the methylene blue index because I can at least do that conceptual planning all the way through. The Atterberg limits are really good for this is what I actually have, and I don't care how I got here. So where do clays impact? We know these have this semi-slurry state, so higher MBI. So we know that the clay content matters in your crushing, milling, scrubbing, conveying, concentrating, backfill. All of these places are where your clays are going to matter. So you'll often have separation problems, you'll have thickening or filtration problems. If you have too much of a high MBI, you'll have transport problems, aka it's too thick and you thought you needed less pumping capacity and now you need more pumping capacity and you have no pumping capacity, so you just add water and then you've just undone everything you did in solid liquid separation and other people get mad at you. So these are all the reasons why you need to pay attention to your clays. Flow problems in backfill, rehabilitation problems on the surface, choking problems, viscosity problems, and blinding problems. All of these things come down to kind of the amount of clay. And all of these things basically, if you are comparing two different operations and one has a higher MBI and one has a lower MBI, the one with the higher MBI is going to have more of these problems. So that's why we say it's a nice pain index, because we know if you have more MBI, you are going to have more pain for all these things. Conversely, if you want to create a nice clay liner for your and have like a nice really low permeability system to encapsulate some nasty waste products, you want that really high MBI. That stuff is gold for you. Yeah. So what are some examples of MBI around the world? So this is from Andrew Vietti at Vietti Slurry Tech in South Africa. He conveniently has measured a bunch of MBIs on a bunch of different samples and can kind of get a sense of the range of materials that he's had to deal with. So we see for oil sands, kind of our average is around that 7, but it, there's quite a range. Mineral sands are a little bit more active in general than oil sands, but in that same range, we have the complicated fact of we also have a whole bunch of organics, and the combination of organics and high clay, that's what makes our life way more painful than it should be. But there's a lot of techniques that can be used from oil sands and imported into mineral sands. Same with diamond mining, that kimberlite tails tend to have a lot of smectites in them. And so again, knowing that you have this more active material that you're going to deal with can help inform a lot of the choices you make. Copper, not so active, usually around 2. Platinum, really not very active from Andrew's experience. The width of the distribution also really matters. So this is particularly important for anybody trying to give a process guarantee to a company doing these things. They'll send you a representative sample. So let's say they give you a sample of an MBI of 7. Well, that's representative. That's true. But it could be up to 22. And let me tell you, your process guarantee that you've designed for an MBI of 7 will not hold if they're feeding you something at an MBI of 22. So kind of being able to put some caveats around feed properties is probably a really good thing if you're trying to give any process guarantees. So yeah, we can use this MBI to estimate the surface area and therefore our dewatering of tailings. as I said, their liquid limits are around that 14. So what does that mean in terms of the solids content that we might achieve at this liquid, like to achieve that liquid limit? Well, if I am at an MBI of 5, which might be a low end of the oil sands region, I would expect to sort of see that liquid limit somewhere in the 65% range. And that's kind of around where we start to see it. And we should be able to maybe get dewatering kind of close to there, but probably not better than that. If my MBI is in the 10 range, which is actually very common for a lot of the fluid tailings that we're treating, I'm not going to be able to get it to be more than 50% solids. And I will say most of the tailings that we're dealing with are in between these two states. And so you can see, well, if I have an MBI of 5 and I get to 65% solids, I'm great. You're like, okay, well, I should always get to 65% solids. But now I have MBI at 10. Well, no, I'm not going to get to 65% solids. I'm lucky if I get to 50 for the same amount of dewatering force and energy and all the things. And heaven help me if I'm trying to deal with something that's an MBI of 30, I might be lucky to get to 33% solids. And that's why that matters to tailings planning. And we can see this across the mineral tailings versus oil sands tailings and kind of where different technologies sit. So there's this lovely little graphic that was shared at the PACE conference about conventional tailings, going to thickened tailings, going to paste, going to cake. And they said, oh, okay, this is my rheology, 5 to 20, 100, and 800. Cool. And then they gave us solids content. And I'm like, no. The rheology is correct. That's where your cutoffs are. But where that solids content is going to be dependent on how much clay you have, because that's what's actually controlling your rheology. And so you can see for this kaolinite slimes and grits, where they put quite a bit of grit in, they were able to get to an underflow stress of about that 1 kPa at about 65% solids. Where in oil sands, when we're dealing with something that's just a pure fluid tailings, we get to that 1 kPa way down at that 55% solids. So everybody in oil sands is like, okay, well, I put in a thickener. I put in a high rate thickener. I'm supposed to get to 50% solids with my high rate thickener. And yet the experience is usually we're at like 30%. And that's if we have enough sand. So you have to respect the clays. So these key differences in how these things behave really depend on how much coarse material you have, what your clay content, and I advocate MBI, your water chemistry, and of course, bitumen content, because all of those things will influence your yield stress. And that's really important because, of course, when you care about tailings planning, the part that you really care about is how quickly can we dewater to be around this liquid limit? Like, you ideally, from a tailings planning perspective, want to dewater your tailings to get to that liquid limit. And then, because then now they're solids and now it's the geotech's problem and they can deal with them, is the general rule of thumb. Usually we give them something that's not quite solid. We give them something wet of that liquid limit a lot of the time. And then they're like, well, how long is it going to take us to get to this part? And we're like, I don't know, maybe a year, maybe 10 years. I don't know. It depends on so many things. And so you can see why it's really important if we can get them there, because again, the volume that you might be predicted to hold, if you designed your containment that you were going to get to 60% solids, you only need 0.1 cubic meters to hold 100 kilograms of this solids that has a specific gravity of 2.65. Great. But if instead of 0.1, you're finding your solid liquid separation process can only get to 40% solids, well, now you need double that amount of volume because you're at like 1.8, 1.9 cubic meters per 100 kilograms. Doubling the storage capacity that you need after your mine is built is a big no-no. They're like, don't do that. What are you doing? And yet this is what happens all the time. They're like, can we raise the dike? Can we please raise the dike? Can we find another tailings pond? no, don't do that. Plan to understand this variation, embrace this variation, and look at like a good stochastic model of your overall mine plan. And that's where MBI can really help us. So yes, we know that we can easily get to that 100 Pascal range with typical dewatering, but we can't go very much higher with typical dewatering limits. And that's why it's really important to understand all these. And I just thought of a better graphic for this. So hopefully I can remember this tomorrow when I might have the capacity to do this. But anyway, so key takeaways from today. Tailings volume prediction is the core of tailings management because that's really all that you care about when you're doing tailings management is where am I going to put the stuff? And is it going to stay where I put it long enough for the geotechs to take over? And can I just build stuff on top of it? Like, so if it's solid, I don't care, it's fine. That's the general rule of thumb. And I'm oversimplifying, but that's the core. Like if you can get your volume management down, you win. You win on so many levels. But what often happens is that dewatering technologies fail because the clay content increases as the surface area of your clay-rich streams increase. So this is particularly important because you always start your mine in the best ore grade. And then